This lesson will be about the normal distribution. We want to get some basics down and then talk about the empirical rule. So first of all, our objective is that I can use the normal distribution to gather information. Some notation we use when we're talking about a normal distribution and we talk about the mean, if we're talking about a sample of data that we gather and we get the mean, we often notate that with an X with a bar over the top. That means we've gathered all the data, added them together, divided by the number of data pieces, and then gotten the average. The population, though, oftentimes when we list that one, we use a Greek letter mu. So it will show that that's the actual population mean if we were to gather everybody's data in the population. Same with standard deviation. Oftentimes when we do standard deviation, we'll say for the sample, the standard deviation, we'll use an S with a little x, saying we found the standard deviation for all the x values for it. This is the measure of spread, whereas the mean is the measure of central tendency in the data set. Whereas the population, when we have the standard deviation for the entire population, if we gather all that data, that would be using the Greek letter sigma. So a little Greek letter sigma will represent the standard deviation. Now, when we do a normal distribution, we have a thing called the empirical rule. A normal distribution is a symmetrical distribution that can help us gather information about that data set. And what we do is we recognize that the mean is right in the middle. Every symmetrical data set, our mean is right in the middle, so that we're going to list this with the mu as our data, our entire population mean. And then we go with measure of spread as how wide the data set gets. Now, what's nice to know is in a normal distribution, we can predict information. For instance, if we go one standard deviation in both directions from the mean, so one standard deviation above it, so it's mu plus sigma, and this is mu minus sigma, the data inside of that set of population is about 68% of the data will lie in that area of population. And then when we go two standard deviations out, so if we go out to here and go with mu minus 2 sigma, and over here go with mu plus 2 sigma, if we have that data set, we get about 95% of all the population will fall in this part of the normal distribution. And then lastly, if we go 3 standard deviations out, we've captured almost the entire population, because 3 standard deviations is 99.7% of the population. So it's plus 3 sigma over here. If we go symmetrically over here with mu minus 3 sigma, the population between these two, the amount of data that falls into that part of the data set is about 99.7%, which is virtually all of the population will fall inside of that. So an example of that is if we talk about newborns, if we use an actual data set. Newborns, the mean for newborn weight, so if you weigh the newborns as their birth weight, their mean is about 7.5 pounds. Okay, and then their standard deviation is about 1.1 pounds. So what that tells us is when we look at that, we can tell that if we go one standard deviation above, so that would be from up to 8.6, and if we go one standard deviation below, so take the mean and subtract the standard deviation, and that would get us to 6.4, about 68% of newborns will fall into that range of values as a normal distribution. Now, a sample might be slightly different. If you take a hospital, that sample might be a little different, But overall, the population, this has been shown to be the mean and standard deviation. And if you want to gather all the way up to 3 standard deviations, so you would take this and you would add on 3.3, because that's 3 standard deviations up. So that would be 10.8 pounds. And on the lower end, we take and subtract 3.3 from that, and that would be 4.2. That weight range, you're going to capture about 99.7%. Now, there are outliers outside of that amount, but that's the general rule. What the empirical rule helps us to do is gather information about that normal distribution. So now we'll take the normal distribution and talk about what's called the standard normal distribution. What this will allow is it will allow us to compare different normal distributions what it ends up doing is it takes the mean and the standard deviation and standardizes it into a graph where 0 is the mean, it's the middle of the graph, and the number of standard deviations you are away from the mean, that's called a z-score. So the phrase z-score is going to become very important in helping us calculate information with normal distributions. So what we'll do in order to calculate a z-score, you're going to take whatever data value you have, you'll subtract off the mean, because that's the middle of the graph, of our symmetric graph, and you'll divide it by the spread, which is the standard deviation. So this is the formula we'll use to convert it. Every normal distribution can be converted into this standardized version called the standard normal distribution. So we use our birth weight example. If we have our mean as 7.5 pounds and our standard deviation is 1.1, what you do is, let's say that we have a baby that's born that's 8.3 pounds, okay? So a newborn, the weight for it is, so for our example, we have an 8.3 pound newborn. Now to figure out the z-score for this, what we're going to take is that data value, 8.3, subtract off the mean, which is 7.5, and divide by the standard deviation, which was 1.1. So you got to make sure you take your calculator and you take 8.3, subtract off 7.5, get what that equals, that's 0.8, divide by 1.1, and I get 0.7272, etc. So I'm going to say approximately 0.73. That is the z-score. It lies just between 0 and 1, somewhere in between 0 and 1 at about 0.73. That's where it lies on the graph of our normal distribution. Let's say we have one below the mean weight. So let's say we have a newborn that is 6 pounds. Again, all you do is you find your z-score by taking the 6 pounds, subtracting the mean, which is 7.5, and dividing by the standard deviation. So if you take 6 minus 7.5, you get negative 1.5, and divide by 1.1, the standard deviation, you get a z-score of about negative 1.3636. It keeps repeating. So I'm going to say about negative 1.36 for our z-score. So it's going to fall over here between negative 1 and negative 2, how far out it falls. So what you need to do in the basics of the normal distribution is understand that the mean is in the middle, standard deviations measures the spread, and you have to think about, for instance, 1 standard deviation away from the mean is about 68% of the population, And then you can compare different normal distributions by converting to a z-score by using this formula, data value minus mean divided by the standard deviation. It gets you a z-score which is standardized among all standard deviation, among all normal distributions.